Imagine scientists making microscopic diamonds smaller than a grain of sand levitate inside a vacuum chamber. No magic tricks, just mind-bending physics. These aren't ordinary diamonds. They're at the heart of experiments probing the universe's deepest secrets. By floating these tiny gems, researchers hope to bridge the gap between two of physics' most important theories. Watching how these diamonds behave could reveal clues about the very fabric of reality. It's science that's as dazzling as it is profound, using the sparkle of gemstones to explore the mysteries of space-time. We'll see how lasers and magnetic fields turn scientists into modern-day magicians, suspending diamonds in midair. And we'll discover why diamonds are the superstars of this research, helping us ask the biggest questions in physics. This is the story of levitating diamonds and their quest to solve the ultimate cosmic mystery. To see why floating diamonds matter in the grand scheme of things, we need to delve into a problem that has baffled physicists for decades. We need to tackle physics' biggest puzzle, the search for a theory of everything. Einstein's general relativity elegantly explains gravity for massive objects, planets, guiding their orbits and dictating their interactions, stars, powering their nuclear furnaces and shaping their life cycles, galaxies, holding them together in vast cosmic structures. By describing how mass warps space-time, creating the force we perceive as gravity, it's a beautiful and accurate description on a large scale. Quantum mechanics, meanwhile, offers a completely different perspective. It rules the tiny world of atoms, governing their behavior with astonishing precision, and particles, dictating their interactions and properties, where things can be in two places at once, existing in a probabilistic haze until measured, and linked across distances through the bizarre phenomenon of quantum entanglement. Both theories work brilliantly in their own realms, providing incredibly accurate predictions, but they don't agree with each other, creating a fundamental conflict in our understanding of the universe. Relativity breaks down at quantum scales, failing to accurately describe the behavior of gravity at the subatomic level, and quantum mechanics doesn't include gravity, treating it as an external force rather than a fundamental aspect of space-time. This leaves a huge gap in our understanding, a missing piece in the puzzle of the universe, especially in extreme places like black holes where gravity is incredibly strong and quantum effects are significant, or the Big Bang, the very beginning of the universe, where both quantum mechanics and gravity played crucial roles. Scientists are searching for a unified theory of everything, a single framework that connects the very big and the very small, seamlessly integrating general relativity and quantum mechanics. Cracking this code would reveal how gravity works at the quantum level, providing insights into the fundamental nature of space-time and answer fundamental questions about space, time, and reality, revolutionizing our understanding of the cosmos. That's where levitating diamonds come in, offering a potential pathway to explore these profound questions. These tiny crystals are helping scientists design experiments, pushing the boundaries of what's possible in the lab to test if gravity itself is a quantum force, exploring the interplay between gravity and quantum mechanics in a controlled environment. If successful, they could provide the first experimental clues, offering tangible evidence to unite the two greatest theories in physics, paving the way for a deeper understanding of the universe. The quest for quantum gravity is one of science's most thrilling frontiers, a journey into the unknown that could reshape our understanding of reality. And it all starts with a floating diamond, a tiny crystal holding the key to unlocking the secrets of the universe. Why diamonds? What makes these precious stones so much more than just symbols of luxury and enduring love? Because they are not just beautiful, they're nature's ultimate high-performance material, a testament to the power of simple elements under extreme pressure. They are a marvel of engineering, crafted by the Earth itself. Diamonds are incredibly strong and stable, boasting unparalleled hardness, all thanks to their tightly bonded carbon atoms arranged in a perfect tetrahedral lattice. This unique structure gives them their exceptional properties. This rigidity makes them perfect for detecting the tiniest disturbances, acting as incredibly sensitive sensors for the most subtle changes in their environment. Scientists can now create nearly flawless diamonds in the lab, replicating the Earth's processes with incredible precision. But the real magic, the key to their quantum capabilities, comes from a special defect, the nitrogen vacancy NV center. It's a tiny imperfection that unlocks a world of possibilities. This NV center acts like a tiny quantum sensor, a nanoscale device capable of detecting the faintest signals, sensitive to magnetic fields, allowing scientists to measure magnetic forces at an atomic level, temperature, and possibly even the subtle ripples of space-time, the elusive gravitational waves that Einstein predicted. Using lasers, researchers can control and read the NV center's quantum state with incredible precision, manipulating and observing the quantum world within the diamond. The diamond's transparency allows light to pass through, essential for levitation and measurement, enabling researchers to probe the NV center without interference. With strength, purity, and built-in quantum sensors, diamonds are the ideal tool for probing the quantum nature of gravity, venturing into the realm where quantum mechanics and general relativity meet. They're not just part of the experiment, they are the experiment, the central component in a quest to understand the universe's deepest secrets. These tiny crystals are robust, sensitive, and ready to explore the universe's deepest mysteries, from the smallest quantum fluctuations to the grandest cosmic events. That's why diamonds are the superstars of quantum research, shining brightly not just as gems, but as tools for scientific discovery. Their unique properties make them the perfect bridge between the quantum and classical worlds, allowing us to observe and manipulate quantum phenomena in a tangible way. And they're helping us push the boundaries of what's possible in physics, opening up new avenues for exploration and understanding of the fundamental laws of nature. Making a diamond float seemingly defies gravity, but it isn't magic at play here. It's a testament to human ingenuity and a deep understanding of physics. It's optical levitation, a technique that harnesses the power of light itself to counteract gravity's pull. The process begins with scientists carefully placing a nanodiamond, a diamond of incredibly small dimensions, into a specialized vacuum chamber. Then they introduce a highly focused laser beam, directing it upward from below the diamond. This laser beam is composed of countless photons, tiny packets of light energy, which exert a force on the diamond, pushing it upward. This upward force counteracts the force of gravity, effectively holding the diamond suspended in place, seemingly defying the natural order. However, the environment isn't perfectly stable. If the diamond drifts even slightly from its designated position, the laser's intensity is precisely adjusted to nudge it back towards the center, ensuring its stability. This creates what's known as a stable optical trap, a region of space where the diamond is held securely by the forces of light. To further minimize any residual motion and achieve even greater precision, researchers employ a sophisticated feedback system. This system utilizes a second laser, carefully calibrated to track the diamond's precise position in real time. Based on the data from the tracking laser, the system makes minute adjustments to the main laser's power, ensuring the diamond remains nearly motionless. This level of control brings the diamond incredibly close to its quantum ground state, the lowest possible energy state. In this state, the diamond is almost perfectly still and remarkably isolated from any external disturbances. Within this meticulously controlled and pristine environment, researchers hope that even the faintest signals originating from the elusive realm of quantum gravity might finally be detected. But the story doesn't end with lasers. Magnetic fields can also be used in conjunction with this setup, providing a means to precisely control the spin of the NV center, a unique defect within the diamond's crystal structure. By skillfully combining the power of lasers with the precision control offered by magnets, scientists are effectively creating a tiny, levitating quantum laboratory suspended in midair. This incredibly sophisticated setup is sensitive enough to allow researchers to probe the very fabric of reality and explore some of the most fundamental questions in physics. It's a remarkable feat of precision engineering and scientific innovation, not a mere illusion or trick of the eye. The result of all this effort, a tiny diamond, gracefully suspended in mid-air, seemingly defying gravity, poised to unlock some of the universe's deepest secrets and revolutionize our understanding of the cosmos. That's the real magic of modern physics, turning seemingly impossible feats into reality through knowledge and innovation. With a levitating diamond, scientists can attempt to detect the faint hum of quantum gravity. Some theories suggest space-time is a frothy, fluctuating foam at the smallest scales, creating tiny, random jiggles everywhere. These fluctuations are almost impossible to detect unless you have an ultra-sensitive floating diamond. Researchers cool the diamond to its quantum ground state, making it as still as possible. They put the NV center's spin into a quantum superposition, pointing both up and down at once. If space-time is fluctuating, it could disturb this delicate state, causing the superposition to collapse. By measuring the spin after a short time, scientists look for unexplained changes. If all other sources of noise are ruled out, any disturbance could be evidence of quantum gravity at work. Detecting such a signal would be a groundbreaking discovery, proof that gravity is a quantum force. These experiments are challenging, but they offer a bold new way to test the universe's deepest mysteries, all with a diamond floating in a beam of light. The search for quantum gravity has never been so elegant or so small. Levitating diamonds open a new window into the quantum classical boundary. Scientists are working to put entire diamonds into quantum superpositions, existing in two places at once. If successful, they could test whether gravity collapses these superpositions, revealing how gravity and quantum mechanics interact. These experiments also probe whether space-time is smooth or made of tiny, discrete units. Diamonds could even help detect dark matter, acting as ultra-sensitive cosmic sensors. By pushing measurement limits, these floating crystals become versatile tools for exploring new physics. They're not just testing one theory, they're building a platform for discovery. The smallest diamonds may answer the universe's biggest questions. Quantum gravity and levitating diamonds might seem distant from daily life, but their impact could be profound. The quest to understand reality's building blocks is part of humanity's drive to explore and discover. Past breakthroughs in fundamental physics led to technologies like computers, lasers, and MRI machines. The tools developed for these diamond experiments could spark new advances in medicine, navigation, and quantum computing. Today's blue sky research is tomorrow's world-changing technology. The journey to understand gravity's quantum nature will shape the future in ways we can't yet imagine. Sometimes the biggest changes start with the smallest experiments. The field of levitated quantum systems is advancing rapidly. Next steps include cooling diamonds even closer to absolute zero and mastering full quantum control. Researchers hope to scale up, creating arrays of levitating diamonds to simulate complex quantum phenomena. Other materials, like silicon spheres, are being explored to expand the quantum sensor toolbox. The ultimate dream tabletop detectors sensitive enough to hear the quantum vibrations of space-time itself. These advances could revolutionize how we study gravity, black holes, and the early universe. The future is bright and sparkling. Levitating diamonds are just the beginning. From jewelry stores to physics labs, diamonds continue to inspire awe. Their unique properties make them perfect for probing the universe's deepest mysteries. Levitating diamonds represent a new era of precision in experimental physics. Instead of building bigger machines, scientists are isolating tiny systems to detect the faintest cosmic whispers. Each experiment pushes the boundaries of what we can measure and imagine. The quest to unite gravity and quantum mechanics is our attempt to read the universe's rulebook. These sparkling messengers offer a glimpse into the unknown. Sometimes to see the biggest picture, you have to look at the smallest things.